This is our Chapter 7, Lessons 1 and 2 outline for AP Stats. We're looking at sampling distributions. And what is a sampling distribution? So some basic bare bones here is that the parameter, starting with P, comes from the population, also starting with P. So that's a number describing the population, whatever it is we're trying to measure. Whereas a statistic comes from a sample. So generally we take a statistic from a sample because a sample is much smaller than the whole population, and the goal is to estimate the true parameter of the population. An example would be if we looked back to the last election for President Obama, and we took a stratified random sample of every county where voting took place. The samples would be the people that actually got picked to get their opinion on who they voted for, and the statistic would be the percent or the proportion that voted for Obama of that sample that got chosen. Now we'd be trying to set that up in a way, in an unbiased way, so that we can estimate, so that it's a large enough sample to estimate the parameter, which is the actual amount of people, that proportion of people that would vote for Obama from the whole population. So again, that is basically within mind that we want to know the parameter, but it's hard to measure the whole population. Even the census, which tries to measure the whole population, it's very difficult and time-consuming. So the trick here being P for parameter, it's from the population, P for population. S for statistic, statistic is from the sample. They'd both be measuring the same thing, for example, the proportion of voters that voted for Obama, except for the statistic would be that those chose the proportion from the sample, and the parameter is what we're trying to estimate from the true population. A population distribution would be what we want to know, the actual proportion that voted for Obama. So the actual values of people. So it's a graph of the parameter, you know. A sampling distribution is a sample, so the statistic, and it describes all values of the statistic in all possible samples of the same size from the population. Usually, since this is all possible samples of the same size, which trips some students up, so be careful with that. Usually we try to get an estimate of the sampling distribution. For example, if we took 250 samples using software and then found the average, that would be estimating the sampling distribution. As that number increased, to be a true sampling distribution, it would have to be all possible samples of the same size. So if we were sampling 30 from a population, it'd be all possible combinations of 30. Now thinking back to permutations, think if you're choosing from a population of 1,000, think about how many ways you can combine combinations of a sample size of 30. An incredible amount. If you'd like right now, go ahead and do 1,000 and then go to Math PRB and choose R, 30. So, and if you do that, you get about 2.43 times 10 to the 57th combinations of 30 of sample size 30 from a population of 1,000. So because that is so many different, every possible combination, the sampling distribution, we say it's an unbiased estimator of the parameter, meaning the mean of the sampling distribution equals the mean of the population distribution, because it's every possible sample of the same size. So unbiased means that it's giving us the same mean as the population. It's a good estimator. Biased would be it's not a good estimator. The two means are not equal. So the mean of the sampling distribution would be equal to the mean of the population distribution. Now, this would not occur in our sampling distribution if, for example, we didn't take a stratified random sample. If we had a sampling error and we had bias there already. So we would have a biased estimator. Think back to all that chapter 4 material. If for some reason we had bias in our questioning or other bias involved. So an unbiased estimator, which is, that's the goal ultimately, because we want to know truly that the result we get from our sample statistic is the same as the population parameter, because that's what we're trying to find. So we want to avoid biased estimators and lean towards unbiased ones, which is what we've learned how to do all year. The variability of a statistic is how much it varies on average. So this is two ways we solve for the variability, for the standard deviation of our statistic. What this basically tells you is that a proportion that's closer to 50% can have greater standard deviation, also greater variance. Because you've got more values it can go up and down with. A proportion closer to 1%, for example, would have a smaller standard deviation because it can't get smaller than 0%. 0% is the smallest it could get. This also tells us that our sample will tend to vary less with a larger sample size. And the law of large numbers also told us that we looked at. The larger the sample size, probability tells us that the more likely we are to approach the true probability, or the true proportion that we're aiming for here. So a larger sample size allows us to get a smaller standard deviation. That would allow us to get a better estimate of the true parameter, which is the goal of everything we're going to be studying here in the second semester. So we want to choose a statistic with low or no bias and minimize the amount of variability to get a good idea, a small interval of values that the true parameter, whatever we're trying to estimate, could be in. So with that in mind, please look over the 7.1 outline and pause here and then answer this free response question. So we're trying to determine who has the support of San Francisco for the 2016 presidential election. We decide to conduct a stratified random sample of 10,000 registered voters and a proportionally representative sample. We're trying to minimize bias here. I want you to identify the sample and the statistic, the population, and the parameter. So overall, you find that this information is key. You find that 5,900 out of the 10,000 contacted support candidate A, that's 59%, with the remainder supporting candidate B. In reality, 57% of all San Francisco supports candidate A and the remainder supports candidate B. Your job that you were assigned to was to estimate the true proportion of voters who support candidate A. Using this information, I'd like you to write these 4 words in your answer: sample, dash, and then write what the sample was. Statistic, dash, what is the statistic? Population, dash, what is the population? And parameter, dash, what is the population? Look back in the video, take a look at our vocabulary, and then also please take a look at the 7.1 outline. Pause and answer this, and then 7.2 is coming. So 7.2 is the same idea about sampling distributions, but specifically for sample proportions, which is what the free response question you just looked at was. So specifically looking at proportions, sampling distributions that try to estimate a true proportion. So p-hat is what we're going to use to refer to our sample statistic, the variable for it, not the actual value. The sampling distribution of p-hat describes how it can vary in all possible samples of the same size from the population. And the mean is equal to the population proportion p. So it's an unbiased estimator, meaning if it's a sampling distribution, it's all possible samples of the same size, so the mean of the sampling distribution and the true population distribution will be the same. Here's how we measure the standard deviation of p-hat, of the sample proportion. So we can only use this formula if less than 10% of the population is sampled. This is what we looked at in probability. When we sample more than 10% of the population, the probability of choosing certain individuals changes too much for this to work. As we get a larger sample size, but less than 10%, the standard deviation gets smaller. We see that because there's an inverse relationship between n and the standard deviation, because n is in the denominator. Larger samples have lower standard deviation, so that's why people want to poll more people, because they can get a better idea of a smaller interval where the true proportion lies. When the sample size n is large, the sampling distribution of p-hat is close to a normal distribution. So we can go ahead and check that by multiplying the sample size by the proportion and making sure that's greater than or equal to 10. And the sample size times the quantity 1 minus the proportion, or the complement of the proportion, to make sure that's greater than or equal to 10. So those are our conditions for the sampling distribution, which we'll check in the plan portion of our problems in this section. So you'll state what the proportion we're trying to estimate is, p, and p-hat is what we're using our sample to measure that. We have to check to make sure random, normal, and independent conditions are met. So in the plan step, you'll write out random, and if we have an SRS, then a simple random sample, that means we'd have an unbiased estimator of the true value, the true parameter, and the mean of our sampling distribution, which is the mean of p-hat here, equals the mean of the true population. So that's unbiased estimator, or SRS. The random condition says SRS is the same. That's similar to center, because the mean of the population distribution is equal to the mean of the sampling distribution. Normal condition. If the population is approximately normal, you'd be told that in a problem I'd give you, or in real life we'd need to know that, then we're good. So if you're told the population is normal, we're good to go. If not, then we have to have the sample size be greater than or equal to 30. And that greater than or equal to 30 condition is for sample means. For sample proportions, we check this condition, that NP, so the sample size times the proportion is greater than or equal to 10, and the sample size times the complement of the proportion is greater than or equal to 10. And that's the shape. So we can know the shape is approximately normal and use our calculations, which we'll do to make a confidence interval for the true proportion. Independent condition, to make sure things are independent, we have to sample less than 10% of the population, which is just like we looked at before with binomial probabilities. Now these conditions are really essential and a huge sticking point of not only this chapter, but the remainder of what we do throughout the year. So it'd be good to sit with these now, go over them, and then come to class with any questions you may have about either of the three. Remember that this n is greater than or equal to 30 will be for sample means, which we'll look at in 7.3. Pause now, look over the 7.2 outline, look over your vocabulary, and then answer this multiple choice. Okay, on December 7th, 2012, President Obama's rating was at 57% according to an Associated Press GFK. They used an SRS of the population to poll 10,000 people. If President Obama's actual approval rating was 55% of the entire nation, then which of these is correct, showing the parameter, the statistic, and that 10% condition? So look back in the video, look at the 7.2 outline, and then submit both of these answers, please.